Alright, in the next couple of videos, what I'm going to try to do is make sure that you understand moment of inertia. But I realized that in order to make sure that you really understand what that is, we first have to make sure that we understand torque. And the equation for torque we know is R times F. However, I never actually went through how we get R times F is equal to torque. I just kind of said, you know how doors work, you know how wrenches work. The greater the distance from the axis of rotation, the greater the effectiveness of the force at causing twisting. And that's a very practical way to look at this, how we get R times F. But it doesn't prove that it's R times F and not like R squared times F or R times F squared. So how do we know that it's exactly R times F? To get into that, I've set up two situations that are nearly identical. We have a long, thin rod, and we'll treat the rod itself as massless in this case. And we put a mass M at the end of the rod. Each case, the M is a point mass. And we're going to apply a force to the rod. In the first case, case 1, we're going to apply that force at a distance L from the axis of rotation. In case 2, we're going to try to apply it at exactly halfway along the rod, so 1/2 L. And we're going to look to see what this does. Specifically, we're going to look at the work done in each case. So if we look at the first case, we know that work, and this is just generic, so I'll just write down what work is. Work is equal to force times a distance. Now, in these cases, let's say that we have an object and it rotates through some particular angle, which I'll call theta. And this is also going to rotate through the same angle theta. Okay, so we're going to move it through the same angle theta in each case. And it shouldn't come as a great surprise that the mass then, if we're moving this through the same angle theta, the mass moves through a particular distance. And this is something that we've talked about, that the arc length here, the distance that it moves, our delta x, so to speak, is equal to the angle, theta, times the radius, which in this case I've defined as L. So in both cases, we're going to move the mass through the same distance. However, when we're talking about work, we're talking about the distance that the force moves. So there might be a difference between these things. I'm just going to rewrite this now as F times theta times L, where this is in place of the linear distance. We're describing the linear distance in terms of theta and L. Now in case 1, where we do the work for the first case, it is just F times theta times L. But in case 2, everything's the same except for one little thing, which is that our force only moves through half the distance. It still moves through theta, right? It's moving through that same angle. But the L that's involved, or the R that's involved, is just going to be 1/2 L. So I'm going to get 1/2 F theta L. And what this shows us is something that will end up being fairly useful to us, which is that the work of the first mass is equal to 2 times the work done on the second mass. That's not a 2. Okay, so this is a relationship that we're going to use. We could also rewrite this as or work 2 equals 1/2 of work 1. In any case, we applied the same force. The mass moved through the same distance, but we did half as much work in this case because our force was being applied for half as much distance. So now let's take a look at what this means for the mass. So let's focus on mass here. If we focus on the mass now, before I scroll down there, we should note that the mass is moving through the same distance each time. So that's one of the things that is important for us to recognize, that theta 1 equals theta 2. And let's just say that in both cases the initial velocity is 0. It's not actually moving anywhere to start with, and I can write that as initial linear velocity also 0. I'll try to keep it linear as much as I can. Now we know that the works are related to each other in this way, but we also know that generically work is equal to 1/2 mv squared minus 1/2 mv initial squared. And in this case, because that's 0, right, we can just make that equal to 0. So we have work equals 1/2 mv squared. That means that v is equal to the square root of 2 times the work divided by the mass. Now in the case of our first mass, so V1 is equal to the square root of 2 times work 1 divided by m. In the case of our second mass, V2 is equal to the square root of, well, 2 times work 2. But remember that work 2 is only half as big as work 1. So we actually end up getting work 1 divided by the mass here. So the square root of work 1 divided by the mass. And that shows us that V2 is equal to 1/2 of V1. Nope. It does not show us that. It shows us that it is equal to 1 over the square root of V1. Or I could just rewrite this as V1 equals the square root of 2 times V2. So it's going to go about 70% faster in moving that mass. So this mass will be moving about 70% faster than this mass at the point when they've gotten through that same angle. Now you might wonder, how does that happen? Well, one of the ways that it happens is we have a greater acceleration. Okay, so the next thing that we're going to do is we're going to look at time. So for time, we can find just generically that time is equal to x over v, and this is v average that we have to deal with here. So basically half of the values that we found there. The good news is that this relationship will still hold. So the final velocity of mass 2 is going to be equal to 1 over the square root of 2 times the average velocity of v1. So I can just go ahead. If I wanted to, I could make those averages right now, but I'm going to skip that for now. So if we look at v1 to give us time 1, this is going to be equal to theta, which is the same for both of them, divided by 1/2 of the square root of 2 times v2. Meanwhile, time 2 is going to be equal to theta times 1/2 of v2. So we can see that the times are closely related, but this time 1 is going to be a little bit less. So interestingly enough, mass 1 is going faster than mass 2, and it's doing it in less time. So we know that it's going to be accelerating quite a lot more. And so I'll just do one more step here. So let's look at what that acceleration actually is. We know that acceleration equals the change in velocity per time. And that means that acceleration is equal to, well, our v final divided by the time. And so if we look at A1 is equal to V1, which is the square root of 2 times V2, divided by the time. And the time here is a little bit of a compound denominator. Theta divided by 1/2 root 2 times V2. V2 is, of course, not under the square root. And what that means is that for acceleration 1, we have a square root of 2, and we have a square root of 2 in the denominator of the denominator, which means we actually end up with 4, because I have a 1/2. Whoops, I have a 1/2 in the denominator of the denominator, so I actually end up with 2 v2 squared divided by 2 theta. And those 2's are going to cancel out, obviously, but I'll just leave it there for now. A2 is equal to just v2 divided by 1/2 theta divided by 1/2 of v2. So what we end up seeing here is that we get, let's see, v2 divided by this ends up giving us v2 squared divided by 2 theta. So end result is that our A2 is actually equal to 1/2 of A1. So in terms of what this means, this result occurred when F1 equals F2 and when R1 is equal to 2 times R2. So we get our, write this a little bit differently, A1 equals 2 times A2. So what was different between them? The mass was the same, the initial starting conditions were the same, the forces being applied were the same. The only difference that occurred in this case was that our R1 was twice as great as R2, and that led to the acceleration of 1 being twice as great as the acceleration of 2. And so that's how we end up getting the idea that if we're talking about the sum of torque being proportional to, I want to be careful with what I write there, but proportional to alpha, which is of course the acceleration divided by r. And remember, the mass has the same r in each case. This is the r for the force. Okay, this is all force stuff. So our acceleration would be 1/2 if the r for the force is 1/2, but our r overall is the same. That's the idea there. But we found that the torque is proportional to the acceleration. Well, that's what we expect to occur. And we found that r times f is proportional to alpha, and as a result, we can then say that the torque is equal to r times f. So that's the basic idea behind torque, and why torque is defined as r times f, because it does what we want it to do. It is proportional to the change in the angular acceleration of the object, and we wanted something that fulfills that role of changing angular acceleration. So that's, I guess, the last point with torque, is that force is the thing that causes changes in linear motion. Torque is meant to be the thing that causes changes in angular motion, which is defined by alpha. And it turns out that if we want to find out what is responsible for that, by doing the math, we see that it's actually going to be the r and the f that gives rise to something that's proportional to the angular acceleration. And this can be done in multiple different ways. I could kind of focus on different parameters, but hopefully this gives you at least decent basic idea of why the torque is equal to r times f.